There was a time when the only way to see how good an aerial was going to work was make it or buy it and try it. But now different antenna can be simulated very effectively with software. And MMANA-GAL is a popular package which does a good job and it's free. Steve Nichols, G0KYA, is something of an antenna enthusiast, having written several RSGB books on the subject, and he's now here to give us hints and tips on how to use that program and give us some examples. So it's a very warm convention welcome to Steve, G0KYA.
Hi, how are you?
I'm good, thanks, Steve. How's things with you? We're not far away from each other geographically.
We've just had a rainstorm go past. I think you've had the same one.
We certainly have. We heard it even in here. In fact, I think it might have even come out on the mic if people were listening hard enough. It was really quite a storm, wasn't it? We're about, what, 12 miles away, something like that from each other?
Yeah. But it's a good thing to show that using a MMANA-GAL means you can mess around with antennas without getting wet. So it's a good.
And that's what you call a plug. All right. Well, in a moment we'll be handing to Steve to do this talk, but just a reminder that this is live, and Steve welcomes your questions and comments as well throughout the talk. It's a good idea to ask them during the talk if you can, because at the end there's quite a rush to get them in and we have a limited time at the end. So just enter them onto the YouTube chat. If you have a call sign, if you can enter that as well as your name, then we know how to address you at the end. But now over to Steve, G0KY, to tell us all about antenna modelling with MMANA-GAL.
Thanks, David. Well, as I said, this afternoon we're going to look at MMANA-GAL. That's how I pronounce it anyway. I've heard various people, MMANA-GAL, but MMANA-GAL seems to work quite well. But we're going to look at what a MMANA-GAL is, what you can do with it, how it works, and some of the sort of more practical applications for using an antenna modeling program. But where does this daft name come from? That's the first thing to ask, really. Well, it comes from the authors of the software. The MM comes from Makoto Mori, JE3HHT. It's his original idea, I think. So it's MM Antenna Analyzer. That's where the MMANA bit comes from. And then the GAL comes from the other two amateurs who worked on it, which is DL2KQ and DL1PBD. That's right, Alex. So that's where MMANA-GAL comes from. So if ever you wondered why on earth is it called MMANA-GAL, that's why. So there we go. And the software has been around a while now, and it's just a new edition came out this year, which is edition 3, I think. But this software or this program, also presentation, is based on the version 1 software. There's very little difference between the two. But if you are going to download it, we'll show you where to get version 3 of the software from. But as David said, it's completely free. And I think as radio hands, we like that term. So let's go on anyway. So what is it? Well, it's a free antenna modeling program that's based on the NEC engine, the Numerical Electromagnetic Code engine, NEC 2, I think it is. And it was originally written in 1981 under contract to the US Navy. And I'll show you why in a second, why it was so useful to the US Navy. And if you want more power, there's a Pro version, a MMANA-GAL Pro, $99, or EasyNEC is the most common program that you often see, or EasyNEC Pro 5 at $500. So I think the way of looking at it, MMANA-GAL is, why not try MMANA-GAL? It doesn't cost you a penny. You'll probably find that it will do everything that you want it to do, unless you are going to start your own business in terms of antenna modeling and production. And for me, I've used it for the last probably about 10 years, and it works fine. And it does show an awful lot of things that you wouldn't otherwise see. The trouble is you can't see radio waves. I think that, by making them visible in a program like this, you can actually see where your RF is going. So what does it feature? Well, you can create multi-element antenna designs and test them for performance and matching. You can look at the horizontal and vertical beam radiation patterns as well. You can generate 3D radiation patterns as well, which look very pretty, if nothing else. And then you can actually optimize your design with respect to SWR, gain, front to back, elevation, and current. And also R and JX, that's the more complex way of looking at the matching. What would you need to add to the antenna to make it work better, i.e. an inductor or capacitor. You can also generate data files, so you can do a run for an antenna from, say, 80 meters to 10 meters, output the data that you can then put into a spreadsheet and have a nice graph, and we'll show some of those as well. So it has got an awful lot of power for a free piece of software. And how did we do it years ago? Why were the US Navy so keen to generate this software, the next software? Well, this is a photograph I found when I was researching the book. This is the US Navy antenna test range at San Diego in California. And you can see this massive arm going up over up in the photograph there. And the little model down the bottom right is a ship. It's a ship. And what they would do is they would rotate the ship around, and then they would move a receiver up and down this arc that you can see there to take field strength measurements off the antenna. And from that, they would then work out and draw antenna plots of how well these antennas worked. And so it was helpful for designing the antennas, and also it was helpful for positioning the antennas on ships for gain, if you like, in the correct areas, or at least stopping them from being blocked in some areas. But this antenna test range here is probably about 40 feet tall, I think. Now, you can imagine having to do that day in, day out, just putting a signal on it and moving the receiver up and down that, and then rotating at 5 degrees, doing it again. It probably took all day just to get the data that you needed from one model. So I think that's quite key, because I think if you imagine that you could imagine someone saying, look, can't we automate this? Can't we do something about it? And hence the NEC 2 engine was, or NEC 1 engine was eventually written. But it's not easy software to write. For example, it has to solve Maxwell's equations. Now, anybody who's done a physics degree will probably have shivers going down their spine at the thought of having to do anything with Maxwell equations. So the Maxwell equations at the top, I'm not going to go into what they all mean, we'll leave it at that, but you can see the integral solutions to them at the bottom. So if you imagine having to work out this solution for maybe 10,000 data points on an antenna, and then plotting it all, you'd probably go pretty mad. So hence, we can now do it all automatically in less than a minute. And I think, thank God to the authors for this software for helping us do it. So what do we need to know? Well, there's a number of words we need to get used to when we're using MMANA-GAL. The first one is that the antenna design is made up of straight wires. They're called wires in the antenna description. That's the thing. We can't curve anything. If you want to make a curve, you have to join lots of little straight wires together. And on top of that, you can then include loads, and they can be made up of L or C, in other words, inductors or capacitors, or even combinations, so traps and loading coils as well. So loads, that's the second term we need. And then we need to apply a source, the specific impedance at a point on one of those wires. So wires, loads, and source are the three terms that we really need to understand. I say that we need to apply a source of a specific impedance at a point on one of the wires. Basically, it's set up to work at 50 ohms, but we can change that in the setup to something else. So if we're trying to design, say, an off-center fed dipole, we might want to use a 4-to-1 balun. Therefore, we could change the specific impedance to 200 ohms and to work it, make it match into a 4-to-1 balun. So we can change the specific impedance that we're applying, but by default, it comes out at 50 ohms. So it's wires, loads, and source. And as I said, loads can be traps, so you can have capacitors and inductors put together to create the loads. So how do we use it then? Well, this is the main screen that you run. It's a PC-based program, although as I'll try and show later, you can run it on a Mac, but with some little tricks. But it's a PC-based program, and this is the first screen. There's basically 4 screens you work through. You do the geometry screen where you design the antenna, then you can have a look at what it looks like, then we run the calculations at specific frequencies, and then we look at the Farfield plots. So this is the first screen that you see, and you'll see here we've got a wire that's been added in there. And basically it's a wire, and everything is in kind of Cartesian coordinates. So it's on the ground, and it's 5.17 meters long in one direction from 0, and 5.17 meters long the other direction. So it's 10 meters long. So basically it's a half-wave dipole for 20 meters. And so there we go. That's the frequency we're designing it for, dipole for 20 meters. And it's just a piece of wire. And as I said, 5.17 meters in one direction, 5.17 meters in the other. And okay, so there's the wire that we talked about. We haven't got any load, so we don't want to add any inductors or capacitors to this. And then we have a source, and W1C it says there. And what this means is that we're going to apply the source on wire 1 in the center. W1C means center. So you have Y1 beginning, Y1 center, Y1 end. So we're going to put this source, basically, if you like, it's the coax that you're plugging into this antenna, in the middle of this, and it's on wire 1. Okay. So then we can move on to the view, and this shows you the antenna. And we've got it on the ground, as I said, but we can actually elevate it when we do the calculations. So there's the antenna, and you'll see there is a blue line on that. That's the current curve on the dipole. So you can see it's maximum current in the middle, and it tails off to zero current at the ends, which is exactly what happens in real life. So we've got maximum current in the middle, and tails off to the ends there. And from this, we can rotate it, or we can zoom in to have a look at it. And this is just a dipole, so we're not too bothered about where everything's going. But I thought I would just show you this, how it actually works. Okay, so now we can calculate. So we go to the calculate tab, and we have our frequency at the top that we want to work for. Be careful here when you use it, because ground, you can have an antenna in free space, which is okay if you're in the International Space Station, but not much use on Earth. Or you can have it over perfect ground. And I recommend that you check or tick the real ground, and you can actually change the ground setup to suit your particular ground. This, I think from memory, there's about 3 or 4 different standards that you can choose. And so we've just gone for a basic ground setup there. And I've put this added 20 meters of height. So we're putting this dipole up at 20 meters. You'll see that it says no loss. You can actually change that to copper wire or aluminium tube, to whatever you need. But I'm just telling you this, that these are the things you have to watch. So make sure you don't put something there with no loss. Make sure you choose real ground, and make sure you get the height right. It won't work if the antenna is lying on the ground. It will come up with an error. So once we've got all this set up, all we do is press start, and it will take a second or so just to click through, and then it comes up with this set of results. What I've done here, these are a set of results that I've run 5 times. So every time you run it, you'll get another line come up. So this basically says that our SWR for this antenna is 1.75 to 1. And the maximum gain on this antenna is 7.37 dBi. And you're probably thinking, well, hang on, it's a dipole. How do you have gain? Well, you get gain in different directions on a dipole as well. And the maximum radiation at that height is at 14.6. Now, that's all very well, but you can't actually visualize that too well. So on the next tab, okay, well, we'll just have a look at this one first. This is a plot as well. You can do plots of the SWR, impedance, gain, front to back, and far fields, etc. So it's just showing you that it is resonant at 14.15 megahertz, and at the bottom there, it's just risen a little bit, maybe about 1.7, and then 14.35 band edge. It's still at about 1.7, which is what you would expect to see. Okay, let's move on. Okay, so now on the final tab, the Farfield plots tab, this shows you a kind of a bird's eye view looking down on the antenna. And we've got X and Y there, and you can see that the typical dipole type distribution of the lobes. So we've got the dipole is running along the Y-axis here, and you can see it's radiating at right angles to the dipole. On this side, this is a side-on look, if you like. You'll see that we've got the maximum elevation there, or maximum gain, if you like, is at about, what is it, 14.6 degrees. And then we've got another lobe there as well. Now, we can also click on 3D elevation or 3D plot there to see this in 3 dimensions. But this is useful if you're designing antennas and you want to make sure that your RF is going off in a certain direction. We'll try and show you later. There's a Slim Jim design that's got very, very low angle radiation. But if you want an antenna that is going to for example, be a very, very good antenna for DXing, maybe on the low band. So you want a very low takeoff, maybe about 5 degrees or whatever. This will help you design something, and I'll give you a clue. if you're trying to do that on 80 meters, forget about a dipole unless you can put it up to about half a mile high. You know, verticals are the way to go. But likewise, if you're trying to work around the UK using near vertical incidence skywave radiation on 80 meters, a low dipole works quite well. So you could design a dipole and artificially move it up or down to see what the gain is at various heights. So you can do no end of stuff with the MMANA-GAL without ever getting your feet wet, or getting wet full stop.
Anything else wet, yeah.
Yeah. Okay. Now there's the 3D view, which I think is pretty more than useful, but it does show you, and you can rotate this as well. So it just shows you the 3D view of the lobes that are coming off at 14, 15 degrees. So it's a not bad little antenna. You've got high angle and low angle radiation at that height. As you change the height, these lobes will change dramatically. So it's a case of, as I said, playing with it to get the height you want. In reality, in most places or most homes, I mean, you are kind of fixed in terms of what height you can get. So this will just show you, you know, how it's going to work. And I'll show you now an example of antennas that we've played with and what we found with them. For example, Roger G3LDI has got a rhombic antenna. This is a monster. This thing, I think he's got 4 towers supporting this, and it goes off into the distance. You can just about see the far towers. But he was telling me he used it on 20 meters, and he could work into New York all day long and into the central US. But he was saying he couldn't get on. It didn't work terribly well up to the northwest states, sort of into Seattle or Vancouver in Canada. And so we modeled it for him, and this is what we came up with. And as you can see, it's a very, very, very powerful lobe there into the central of the states. But you know, you've got a couple of nulls here. You've got a null there and a null there. Also down here into Florida, it doesn't work too well either. And he said, well, that's actually, you're absolutely right. It doesn't work too well into Florida. But this is an extreme version of what you can do with a MMANA-GAL to show you just how an antenna works. Normally, you don't really want a pattern like this, but it does show you sometimes why you can design and build antennas that work really, really well in some directions, but others that just don't work at all. For example, let's go through some hard sort of worked examples. The G5RV now is kind of a classic so-called multi-band antenna, but is it really a multi-band antenna? Well, rather than put one up and play with it, which we could have done, but run it through, design it and run it through a MMANA-GAL, and you find some interesting facts. For example, here we see that on 80 meters, it's got an SWR of about 5.5 to 1. So that means it's pretty easy to match with an antenna tuning unit. Well, you also have to bear in mind that this is, one, it's a simulation, and 2, we're talking about the SWR at the feed point. By the time you put 30, 40, 50 feet of coax on this, the SWR would improve dramatically. In fact, if you put an infinite length of coax on one of these things, it would have a one-to-one SWR everywhere. That's just a fact of antennas. But getting back to this then, so on 80 meters, it shows that it's quite easy to match on 50 ohm impedance. It's quite easy to get a good match, one-to-one match with an ATU there. Not too bad on 40. Pretty lousy on 30 meters, 34 to 1. Again, 20 meters, 4 to 1. And in fact, a G5RV is actually designed for 20 meters. Then we go up to 18, it goes to 37.1 to 1, bad news. Down again at 15, not bad at 12, and then lousy at 10 meters, 52.2 to 1. In other words, it's not really a very, very good multi-band antenna. It will work reasonably well on some bands, but certainly not on all bands. And I think Louis Varney just, when he designed it, it was really designed for 20 meters, and the other bands were, you know, we have to bear in mind that when Louis Varney designed the G5RV, we didn't have the WARC bands, we didn't have 12 meters, we didn't have 17 meters, we didn't have 30 meters, so he wasn't really that bothered about them. But obviously, the other point I would make here is it does show that it's not a particularly good match on 10 meters, and I've burned out an ATU trying to tune a G5RV on 10 meters, a Scout Jamboree day once, and this, I think this shows why. So without ever getting your feet wet, your head wet, or anything else, or having to mess around with any wire whatsoever, you can play with the antenna designs and see where they're going to work well and where they're not. What about the W3DZZ? This is another multi-band antenna, which is the trapped dipole. And if we build one of these and run it through a MMANA-GAL, we can see that, as you'd expect, it should have a low SWR on 80 meters, which it does, 1.87 to 1, 40 meters, 2.14. Then it goes a bit awry. 15 is okay, but 20 is not brilliant. And in fact, we come up to 28 megs. It's 35.7 to 1 again. So it's not a particularly good antenna. But you can play with the LC combinations with this and see whether you can improve it or not on particular bands, or with particular directions if you want to rearrange it. That's the other thing about MMANA-GAL. It can help you choose how you are going to put your antenna up. Most people, have 2 trees in the back garden and it has to go between them, and fine, that's okay. But this will show you that maybe some other directions, you'd be better aligning it slightly differently to get your antenna lobe onto the antenna, onto the place you want to work. So what about mag loops? So you can model mag loops, but as I said, you can only use straight wires with MMANA-GAL. So this is a mag loop that I've designed on MMANA-GAL. We did it as an octagon. That was the easiest way to do it. But it just shows you some interesting things. So it shows you that they're very, very high Q magnetic loops and a very, very narrow bandwidth. And MMANA-GAL shows this for us. We can see that the particular frequency we were on, I think it was about 14 megs. There's the SWR curve. So very low SWR, but it is very, very narrow bandwidth, very high Q antenna, which again, we can play with the idea and play with building one in MMANA-GAL and see how it works. And the other thing then you can do is play with different heights. So the mag loop, what you'll find is that they don't have to be that high. If they're mounted vertically, they don't have to be very high. So we can see there at 3 meters high, it works quite fine. And we see that we've got more gain at low angles at 3 meters than you do at 7 meters. At 7 meters, the lobe goes high. So in fact, putting a mag loop up at 7 meters would actually work to your disadvantage. You actually want it a bit lower. And these plots here are at 10 degrees elevation. So again, you can see that I think, let's have a look. Yes, the mag loop runs that way. It runs in the Y direction. So there we can see at 10 degrees elevation that, in fact, it's slightly better at 7 meters, but there's not a lot in it. But in fact, off the sides of the mag loop, that you see that it's a little bit better at 3 meters than it would be at 7 meters. So it's all about compromise. And this lets you play with different heights of antennas to see how they work and whether they're going to work better or not. Now, W5GI, the so-called mystery antenna, was quite popular a few years ago, and I still use one, or we haven't used one. We've used one when we do special event stations up here in Norfolk, the Caister Marconi, International Marconi Day, we use a W5GI. And there's interesting things about this, though, because this is a plot of the W5GI on 28 megs. And you can see you've got some very, very strong lobes there. You've got some very deep nulls as well. So the station that you want to work, if it's on a lobe, great. If it's in a null, no, it's not going to work at all. You're probably about 20 decibels down. Not good at all. What about as an inverted V? So, okay, so instead of actually putting it up and making it into an inverted V, let's try modeling it as an inverted V. And so we model it in an inverted V. And what we find is that, okay, when you model the W5GI as an inverted V, you lose some of the gain, but you do fill in these lobes. So in fact, it looks like the antenna works better as an inverted V than it does as a flat top antenna. And that's quite that's a useful tip to learn, that inverted Vs generally do fill in some of these gaps. They're not quite as loby as they would be if they were flat top. But again, you can play with it and see what you get. Now, what about the Microvert? How many people have heard of that? This is a little antenna, I think it's about 5 foot long, that is quite a clever idea. It's a German guy who invented it. And what it is a loaded vertical. Then he used the coax as the counterpoise. So you have a quarter wave of coax, then you have a a choke to stop the current going past the choke. So you've only got this little 5-foot radiator, then you've got maybe a quarter wave at 40 meters, so 10 meters of cable that comes off it, and then it's choked. So does the coax radiate? Well, you can model the Microvert in MMANA-GAL, and this is what you get. I mean, you can hardly see it. There's this tiny little black dot there, and that's the current distribution on it. So you can see that the current is mainly, this is the counterpoise going off there, the coax going off there. So basically, the maximum current is actually in the counterpoise, not in the little Microvert. In fact, there's a minuscule amount of current in the Microvert itself. So it's suggesting, or MMANA-GAL is suggesting at least, that it's actually the coax that does most of the radiating on this. So it's another way of showing electronically how an antenna works. And let's have this is a more practical example. When I moved into my last house, first of all I threw up a W3 EDP antenna over the roof. So it came out of the shack window there, went up and over the roof, and then down in the garden, was tied off. And it was just a quick and easy thing to get going, and it worked okay. But what I did find is I couldn't work anything south of me. Oh, sorry, no, that's the other way around. I could work stuff south of me, but nothing north. So anyone in Norway, in Sweden, I couldn't work at all. But it's always seemed to be working really, really well down south. So again, if we model that in MMANA-GAL, we got a pattern like this. So you can see that here is southeast, there's southwest, there's south, and then we've got this big null behind where it was that it was going, which meant that it wasn't working terribly well at all into the north. Again, so by playing with MMANA-GAL and an antenna design you've got, you can decide whether it's going to work for you, whether it's going to work in some directions better than others. And what I found here, I mean, from mine, this direction was the States, and it was like okay, but not brilliant. So anyway, I had to come down and was replaced with something else eventually, a much better antenna. But it was an easy way to show where your RF is going. And it's not easy to work out where the RF is going until you actually get something like this, I don't think. Now, why is the vertical, I've said vertical end-fed half wave, but to be honest, it could be a vertical quarter wave ground plane as well. Why is it good for DX? Well, this shows you what you get with vertical antennas. You get omnidirectional radiation, so you get full 360-degree pattern and pretty much low angle. So there's 20 degrees, I think. Here we go, elevation 19.7 degrees maximum. So 20 degrees. Probably get it a little bit lower as well. But this is why it's really good for DX. To have an antenna here that is radiating at low angles in all directions. Some people say that a vertical radiates equally poorly in all directions. I think that's a bit unfair, but I know what they're getting at. But it does show you there's no high angle radiation. So if you have a vertical for 80 meters, you're not going to do very well around the UK because there's no radiation coming off the thing up the top here. It's all low angle, so it probably worked very, very well as a DX antenna. Probably work into the States in the early morning in the middle of the winter, but working around the UK, not too well at all. So again, this is why verticals are good for DX, and you can show it in MMANA-GAL quite easily. 80-meter Wyndhams or off-center fed dipoles, another good way. This is something I modeled, and you can see that I output the file into a spreadsheet and then got the spreadsheet to graph the SWR curves of the antenna. And we've got two here. We've got an 80-meter Wyndham as a flat top and inverted V. So is there any difference? Well, yes, there is. In fact, you find that the inverted V isn't so resonant at, what's that there? Is that about 10 megs, I think? Not so good there. And as a flat top, it actually had a very low SWR, but that wasn't apparent really as an inverted V. And you'll also notice that the SWR minima move not in the same place, so it's changed it very, very slightly. And again, here we've got an inverted V, we've got a low SWR at that point, where it would be higher SWR as a flat top. So again, you can play with these things. There's 15 meters, look, and you're not getting any resonant point there as an inverted V. So you can't just put an antenna up as a flat top or an inverted V and expect it to behave the same way. We showed earlier that by putting it up as an inverted V, you fill in some of the gaps, some of those nulls in the radiation pattern, but you may find the SWR changes, or the minima change depending on what frequency you're on. So I think it's a good way, again, of modeling how an antenna is going to work. And I'll show you now a practical application of this. A 40-meter Windham antenna, so that's a half-wave dipole on 40 meters, but you can usually feed that at about 41.1% along one of the, 33.3% along the wire. So we take a piece of wire that is 66 foot long, 20 meters long, and we break it at the third point, so it's 1/3, 2/3, and then we feed it with a 4-to-1 balun. And you'll see that we get this yellow trace here. So you get a low SWR on 40 meters, low SWR on 20 meters, and then a low SWR on 28 meters, 28 megs. But what happens if you change that feed point? You move the feed point along. Well, what you find is if you feed it at the 41% feed line, so you're now at 41% along the wire, what you find is it makes no difference to the SWR at 40 meters, no difference to the SWR really at 20 meters, but now you're getting 15 meters as well. You've now got an SWR, low SWR point at 15 meters, and again, it's a good point up at 28 megs, 10 meters, it's still going to behave as well. So it just shows you that by modeling this, you can play with things. You can play with the idea of changing the feed point of a Windham, and does it make a big difference? And obviously, yes, it does. And I tested this at the last house, and yes, it did work. Managed to get 15 meters out of a 40-meter Windham, where otherwise it would have had a high SWR if it had been fed at the 1/3 feed point. So are there any pitfalls to using something like MMANA-GAL? Well, yes, there is. I mean, for start, the software assumes your antenna has nothing around it, and real life's not like that. We have sheds, we have buildings, we have trees. All these things can impact the radiation pattern and can impact the SWR figures you're seeing as well. Well, it can't model those, so it's an idealistic way of modeling the antenna, really. And what about your earth conductivity and your dielectric constant? Do you know what they are? For example, if you've got very wet earth, you're going to have a different conductivity rate than if it's dry. So you may find that, and some antennas or ground plane antennas work better when it's wet than when it's dry. But otherwise, how do you know, unless you do some experiments and, with checking the conductivity you saw, you don't know. So you have to guess it. And so you have to put the guesstimate into the MMANA-GAL software. And make sure, as I said, you choose the right impedance. It defaults, actually, by the way, to 75 ohms out of the box. One installation I put in and found it defaulted to 75, so that's no good. You want to change it to 50. And you just do that in the setup. It's not a problem. Also, make sure that the elevation, that you want to test is actually the right one. When it does those plots, it will show you the pattern at the highest point of radiation, or the highest amount of radiation. And you go, oh, that's okay, but that might be at 45 degrees. Well, you want to know it's doing at 5 degrees. So what you have to do is you have to go into the elevation box and say, no, I want to have a look at 5 degrees or 10 degrees and do it that way. So that's a very good tip, I think, is make sure you are checking at the correct elevation. With inverted Vs, you really need Pythagoras to help you. If you're trying to get a piece of wire and now you're bending it, in terms of the XY coordinates, Pythagoras helps a lot. If you don't want to get involved in the maths of these things, it's not too bad. You can actually draw them in using the wire edit function. It's a little bit messy and a little bit difficult to align the things. Other points you can make: PVC coated wire will come out shorter than it's predicted by about 90–95%. So you can produce a marvelous antenna that looks brilliant on MMANA-GAL, and you've got everything sorted. But when you actually build it, you might find it needs to be a little bit shorter. Why? Partly due to end effects, partly due to the difference velocity factor of the wire. And what you normally find is that PVC coated wire it basically slows the electromagnetic wave down through it. So electrically, it looks longer. So you have to make the wire slightly shorter. Not a problem. It could be a problem if you were building a beam of some description with PVC coated wire. But luckily, most beams are aluminium, so they don't suffer the end effects and the problem that you get with PVC coated wire. But it's just something to be aware of, that if you design something with a MMANA-GAL and you're going to make it with a coated wire, don't be surprised if when you actually build it in real life, it's going to be a little bit smaller. The real life SWR values will be far better than predicted, as I said earlier. What you find is that due to coax losses, the SWR figures are lower when you've actually put the 100 foot of coax on and you're measuring it at the other end of the coax. Remember, this is a simulation of what the feed point impedance is like. Well, that feed point impedance could be 30 feet up in the air. It's not practical to read the SWR at 30 feet. You've got to attach your coax and bring it down. So don't be surprised if the SWR figures are not quite the same as predicted. They will be lower. But even so, I mean, I've been using the software now for quite a few years, and it's good. It shows you where the minima will be. It shows you what bands you're going to be able to get in. Shows you by how, as I said, by moving a feed point around, you can get other bands with Wyndham antennas. I think it's a tool worth having. And one more. Finally, don't apply a source. That's your, the source, as in putting your RF onto an angled joint. MMANA-GAL likes you to have it on a straight piece of wire. So even if you have an inverted V, just put a tiny little bit of wire and apply the source to the center of that little piece of wire there. There we go. It's a simulation as well, and real life installations may not behave the way you expect them to behave, because antennas have a nasty habit of reacting and interacting with everything that's around them. So it is tricky. So I think that's it for the pitfalls. Just finally, the sources there. MMANA-GAL software, that's where you get it from, hamsoft.ca. The quick start tutorial, there's the URL for that. Well, I think we'll make the presentation available for people who want to know where these URLs are, because they're a little bit long-winded. YouTube, I think Callum McCormick has done some fantastic videos. There was one that caught my eye. It says easy antenna modeling, secrets 0 to hero in 30 minutes. I think, if you can learn the basics of MMANA-GAL from a video, it's going to be far better than a book. Although, I would promote my own book. Everyone else is doing it today. I don't see why I shouldn't. But yeah, I think with video, it's much easier to understand what somebody is doing. And I think that Callum McCormick's done some really good videos on how to use MMANA-GAL, and he designed the DX commander pretty much with MMANA-GAL, I think. So it shows it does work. Lots of more tutorials online. Just search for MMANA-GAL and you'll find them. And also there's some of these designs for antennas on my blogspot page, g0kya.blogspot.com. So what's that? 39 minutes. So we've got a little while now, David. Do you want some Q&A? Have we had any questions come up?
We have, Steve.
Oh, right.
Yeah,
Excellent.
Thank you very much indeed for that. Yeah, timing, perfectly professional, brilliant. Wouldn't have expected anything else. The first question I think is an easy one, and it's to your right hand, I reckon. Dave Goodwin V9CB says, where can I find that image of the curved tower on the US Navy test range that beautifully illustrates the challenges of assessing the performances of an antenna? I teach ham classes, he says.
Right. Okay. Well,
here it comes.
It's in the book.
Yes. Well, I thought that's what you'd say. Why not?
It is. I think I got it off the internet. I can't remember. I was searching around and found it. I think you have to search for the internet. But I know that San Diego is the U.S. Navy's home, I think, on the Pacific coast, and I know it was there. So search for US Navy antenna test range and you can probably find it on the internet. I mean, I produced this 6 years ago now, so I don't know if it's still there, but I just thought it's a great picture that illustrates everything.
It definitely is. Our friend, the commercial manager of the RSGB, has already put a link up in this stream to be able to download, to be able to order one from the bookshop. And in fact, it's, as you know, it's called An Introduction to Antenna Modelling. Non-members price $10.99. For members, it's £9.34.
£9.34, yeah.
All right.
Yeah.
Radio Gareth says, worth mentioning that there's a graphical input mode for people whose brains don't do coordinates.
Yeah, absolutely. You use wire edit mode, and then you can just draw the wires in. I generally don't prefer it. I mean, that's just the way my mind works, I suppose. But it's easier if you're doing inverted V's or anything that's at an angle, because you know, if you want a 20-meter dipole as an inverted V, how do you work out how long the wire is in XY coordinates? And as I said, that's why you need to use Pythagoras. But go into wire edit and just draw the two lines in and make sure they're 5 meters long, whatever. Test it. If the SWR is a little bit too high or too low, make them a little bit shorter or a little bit longer. So yeah, you can use the wire edit mode.
Okay. We've got, by the way, just to let you know at home, if you're watching and you want any questions or comments for Steve, please put them in now onto the YouTube chat, because we're coming towards the end. But we've got Tony G3OVH who said, I've found that for a 4 or 6 meter Yagi, putting the ground factor in completely upsets the results, even at 11 meter height. I can only get sensible numbers with free space. Can you help?
Oh, that's interesting. Well, for starters, I wouldn't do it as a free space model, because life's not like that. Life doesn't appear in free space. I don't know why he's not getting the right results using a MMANA-GAL, using a ground model. I would suggest that there's something wrong with the Yagi design. The too long, too short, or the spacing is not quite correct. But if you're getting the right result, or the result you want, sorry, not the right result, but the result you want in free space, but not when you put the ground in, that suggests that the antenna design is a little bit off somewhere. That's the only thing I can think. I can't think. Or you've got your ground dielectric set a very, very odd figure. So either use the default settings that come with it, or put some in that are reasonable into the ground settings. But I think that's the only thing I can say. If it doesn't look right in a MMANA-GAL, it's possibly because you know, the design's not quite right.
Okay. Mike G4CDF says, I've modelled a pair of helix antennas at 2.4 gigahertz. Works very well. Use Excel to generate the antenna file.
Very good. I mean, there is the difference between a MMANA-GAL and a MMANA-GAL Pro is the number of wires that you can have. And I think you can have up to something like 4,000 wires with this version, and something like 8,000 odd wires in a MMANA-GAL Pro. And when you think of wires, think, well, what sort of antenna has 8,000 wires? But no, you can build models. So there is a picture of a parabolic dish that's been made in the MMANA-GAL Pro, and it looks like some sort of geodesic structure that's been built. So to model helixes at 2.4 gigs, I think that's very good.
Robert 2E0LBW says, if not covered, can you talk about including traps, please? I'm wanting a 20, 30, 40 half-wave end fed with traps for 20 and 30 meters.
Yeah, I can. I just wondered, do you want me to go to MMANA-GAL and show you how to do it?
If you'd be very, very quick,
okay.
Steve.
Let me give this a whirl.
All right, we'll let you do that. And say just one more little plug to remind you that we're coming. We've got about 6 or 7 minutes left. So if you're dying to ask a question, Steve, don't wait anymore. Just pop it on there on the YouTube chat.
Right. So I've got a MMANA-GAL running, and it's running on a Mac here. I meant to say that someone did email me and say, can you run it on a Mac? And my answer to that was, no, you can't. Well, you can actually. Here we go.
Are you running this under a Windows emulation then, or Parallels or something like that?
Yeah, I'm using it with Wine. I tested it yesterday just to see whether it would work, and it does. So this is a trap dipole for 14, 21, and 28 megs. And you'll see we've got the wire. Let's have a look at the view, first of all. So it's just a wire dipole. But can you see, let me zoom in a bit. Can you see there we've got some different things at these points? You can just see little red dots probably. It's probably a bit difficult. But these are LC traps. So they're LC traps. And there's the value of the inductance. And there's the value of the capacitance. So the LC traps just made with 100 picofarad capacitors, and then coils as well. Q factor of 150. And basically you put this one is at wire 2 beginning. That one's at wire 3 beginning, that one's at wire 4 beginning, that one's at wire 5 beginning. So that's how you do it. You create these things, and then you put them into the design. It looks a lot better when you've got it on your screen at home, because all you can see is little red crosses that show you where these traps are. That's how you do it. And the other thing you can do with the MMANA-GAL is you can actually, you've got a little thing called HF components, so LC match. So we can actually create traps using this program. So you tell it what frequency you want, and then you hit the LC button. There we go, that's the one. And it will actually generate the L and C values that you want for the traps. So it's a way of making manual traps yourself. Just close that to see. But let me just run the now. So we'll just calculate this at what should we say, 14.050. Good. Now if we do the Farfield, well, actually no, we want to do that one. So you can see that we can see the current distribution there on 20 meters. It's using the whole of the dipole. But let's do it at now 28 megs, and we'll show you the effect of the traps. Oh, that one. There we go. So now you can see that the current is just in the position of the first part of the aerial, but there's nothing beyond it. And that's because these traps here are trapping the current, if you like, at 28 megs and stopping it going any further. So that's how you do it. So so you put the loads in here as LC types. So it's
that's just because we've got beginners watching this. That's an inductance and a capacitance.
Yeah, inductance and capacitance of 0.312 millihenries. I think 0.312 millihenries. I can't remember if it's in henries or millihenries. I'd have to look that one up. And then 100 picofarads. And you can play with these values. I recommend that if you're doing anything with traps, you start off with 100 picofarad capacitance, and then adjust this to get the inductance that you, the resonance that you want. But that's how you do it. And you put them at the beginning or end of the wires that you've described up here. I hope that's made sense.
Yeah, I think that's really good. I think Robert would be very pleased with that individual answer. We just wanted to get through a few more, though, if we can, Steve.
Okay.
Chris, G1JXS, says, I've got a small garden. I've not used my MMANA-GAL. Will it model a nested Marconi antenna by G7FEK, which has an offset centre feed point?
I know the G7FEK. I don't know whether I've got one in here. Just close that one down. Yes, it will. It will model it quite well. Let's see, where is it? Don't know if I have. I haven't. Yes, I have. Look at that. Right, G7FEK.
We'll share that screen with everybody at home now.
Okay, let me show you. So that's a G7FEK. It's basically 300 ohm ribbon up here, or 450 ohm ribbon. Then one wire goes out that direction, one wire goes out in that direction. And I can't remember what bands they're cut for. I think that one's cut for 80, and that one's cut for 40 maybe, or even 20. But so yes, you can model a G7FEK. But it's a little bit complicated to do. But I can't remember whether we included this in the book, because the book has a CD-ROM and it's got lots of antennas on it. It might even be on the CD with it. But so if we now take this and there we go. Just do a quick run. Right. So it's not designed to work on 20 meters. Let's see if it's worked on 40. I think it is meant to work on 40. Start. 8-to-1. Okay. And let's try 80 meters. This will probably be better because I think they are designed to work. No, it isn't. Look at that. But yeah, you can design G7FEK. Antennas, not a problem at all.
Okay.
You just have to, what you have to do is you have to produce the, if I do the view and then we zoom in on that, what you'll see is you've got, there we are, it's basically like open wire feeder in the middle there. And so you basically have to produce the open wire feeder, and then once you get to the top, one leg goes in one direction, one leg goes in the other.
Okay, we need to move on to a few other questions, Steve, but thank you ever so much for that. Mike G4CDF says he's also used it to model Yagis with good agreement of pattern, at least with G0KSC data.
Yeah,
Ian says, thanks very much, Ian Monroe. This is GM4VXM. Says, thanks very much for a very watchable introduction. Can you clarify what is meant by adding a straight bit of wire to feed an inverted V. I can't quite envisage what you mean.
Yeah. Oh, how can I draw that? Just see if I don't know if I've got. I don't know if I've got one in here. Basically, have the inverted V. We'll do it with hands. That's easier, isn't it? So you have two wires, comes through a tip, but they don't recommend in MMANA-GAL that you actually put your source at an angled joint. So just separate them out a little bit, put a little bit of wire in between them, maybe 2 inches long, it doesn't matter, and then put the source in the center of that piece there. And they said it works better.
Okay, Mike G4GUG says, I can't have an external aerial. I live in a park home wooden bungalow. It's 28 by 20, gutter height's 10 feet, approximately above ground level. How would a horizontal loop work, and what can I expect fed with CG3000, he says.
Wow, that's a question, isn't it?
It is a bit. There's quite a few bits of that question. If you could, can you cover that fairly briefly?
Oh dear, right. Okay, so your loop antenna, so not a mag loop, but a voltage-fed loop.
Yeah, it says a horizontal loop, yeah.
Yeah.
I think they know that you, as well as this program, I think they know you're quite an
Yeah.
antenna expert, Steve, so I think that's why they're slipping these in.
It needs to be maybe one wavelength at the frequency, lowest frequency you want to work. Then needs to be fed with open wire feeder to the ATU, not coax. Well, you could feed it with coax, you get losses. It would probably work okay. If it's near the house, it'll probably pick up a lot of noise. That's the only thing.
Okay. Stephen G. Sorry, I've got to move on though. Stephen G7 VFY. When will we start seeing new, unique designs of antennas thanks to this sophisticated modelling software? Great question.
Well, we are seeing unique designs. I mean, Justin, just somebody mentioned his name earlier, Innov Antennas has been using software to design his antennas for a long, long time. He uses something a little bit more sophisticated than MMANA-GAL, but he's come up with some very unique ideas and antennas that work really, really well. Some of the Innov Antennas, Yagis, don't have any connections. They work by induction, so very, very clever indeed. And as I said, Callum McCormick at DX Commander has used MMANA-GAL to, I think it was MMANA-GAL he used to design the DX Commander, which is a multi-band vertical antenna, ground plane antenna that works very, very well. So we are seeing antennas being designed.
Something new being invented, yeah. I mean, we're used to seeing all these rigs and things changing with touch screens and everything else and SDRs, but it's good to think that one of the most important bits, if not the most important part of your radio station really is the antenna. So it's lovely to think that there are new innovative designs, isn't it? Tristan, by the way, says it also works great under wine, so as you've said. Bill GM4UBJ says, I've found antenna descriptions saved with the original free version of MMANA-GAL do not work with the latest free version, so it's worth noting and sharing with everybody.
Okay.
So just be a bit careful with that. Eugene, HB9IAS, what is the effective height of my inverted V on a 5-metre mast on top of a 40-metre apartment building?
Well,
is there a quick answer to that, Steve? Because we've got about a minute.
Okay, 1 minute. It's very, very, very difficult to model because you've got an antenna 5 meters up, but then it's over a concrete and steel structure. So this is the problem I was saying, that antenna modeling software can't really model real life. It doesn't really understand concrete buildings underneath it and things like that. So what was the effective height of your antenna? I would guess it's probably, if you try to work it out as if it was 45 meters or whatever above ground, that's a good starting point. But it isn't above ground, it's above concrete and steel, so that will have an impact on the antenna. But you do see some of the issues that arise here. MMANA-GAL can't model real life situations. You'd have to try and come up with a wire model for whatever it's put on, and that would be tricky. So I can't give you an easy answer to that one, I'm afraid. But it's more likely to be modeled at 45 meters than it is at 5, let's put it like that.
All right, that's a good bit of advice. Yeah. And finally, I mean, lots of people said, thank you very much for a great presentation, Steve, as you won't be surprised to know. Chris G1JXS says, many thanks, Steve. I'm going to download MMANA-GAL and have a play right away. Great lecture, he says.
Thank you very much. I mean, I'm very pleased that if it at least gets people to play with it. I think the trouble with some software is you open it up, you have a look, oh my God, how does this work? But if you take it logically, it's quite easy to use. So there we go. Oh, I better not run over because we've got Jim next, haven't we? So,
yeah, that's right. Many thanks, Steve. Thank you very much, Steve Nichols, G0KY. Thank you ever so much for a lovely presentation.
Okay, bye-bye.
Bye-bye.